I'm Jacob Fonseca. You see me in such fine quality chemistry educational epic videos as Potential and Gibbs Guitars, Gibbs Energy, and Galvanic Cells and Electrolytic Cells. Shocking revelation! Okay, today we're going to be looking at electrolytic cells. Okay, we're going to be looking at the free energy that's involved in it and how can we calculate if something is going to be deposited, if it's going to plate onto another metal. So we've looked at galvanic cells. They're fairly common. They're also known as voltaic cells, and they generate electricity, and that's what typically we have in our batteries today. But what about electrolytic cells? Electrolytic cells are the exact opposite. Okay, they need electricity in order to make things happen. Of course, the question comes down to, well, all right, but then what's the real world use of such things? Well, in electrolytic cells, we can go ahead and plate a metal with another metal that we normally would not be able to do. But we can through the process of electrolysis. We can do that, electric plating, if you will. So some everyday examples here. You could take a look at this key here for a moment, and you may notice here that there is some silver on the top, but there's also some yellow there. Well, what's up with that? Well, that would be an example of metal plating. Okay, and we're going to take a look here. We're going to have copper and zinc, and we're going to see, hey, can we make the zinc plate onto the copper? Can we do this? All right, so here's our reaction. Here, our reaction, we have copper, solid copper, and zinc ions will go and get us copper ions and zinc solid. Now we're going to calculate the delta G of this reaction. And we're going to answer the question, will zinc ions plate out in the solid copper in this reaction? Now, some of you guys might be sitting there thinking, wait a minute. When you were talking about galvanic cells, the reverse was true, that the zinc electrodes were slowly breaking down because they were losing their electrons and copper was being plated. Right, for galvanic cells. We're going to try the reverse and see, can it work? Can it be done with this? Okay, well, we have to look at part of our solution here. We need to look at our formula here. The free energy is connected to the cell's EMF, or electron motive force, okay, or electrical motive force. Now, this idea is also involved in AP biology when you talk about respiration and photosynthesis, when you're talking about the electron transport chain and the manufacture of ATP through the F1 particle. Yep, EMF is so involved in that, as well as a pH difference, but that's another topic for another video in another class. Okay. So here we have delta G of our reaction is equal to negative N times F times the E of the cell. Wait a minute, NFE, what's up? Well, delta G is our free energy of the reaction. It's either going to be 0, which in that case nothing exciting is going to be happening. It's going to be negative or going to be positive. Okay? If it's negative, it's going to be spontaneous. If it's positive, it's going to be non-spontaneous. Now, N is the number of moles of electrons exchanged in the reaction. Okay, and F is Faraday's constant. Now, Faraday was a dude who came up with some really mind-blowing things regarding current and electricity. Okay, and this constant that he found, which was about 9.65 times 10 to the 4th coulombs of charge. That's what a coulomb is. It's a charge unit per mole of electrons. Okay. And then E of the cell, that's the cell's potential, where we look at the reduction and the oxidation reaction and combine it together. If the E of the cell is positive, you have yourself a galvanic/voltaic cell. On the other hand, if it's negative, then what you have is an electrolytic cell, which you're not going to get electricity out of it. Okay, you're going to have to put energy into it in order to make things happen. Okay. So our first thing we're going to need to do, we're going to need to break down this redox reaction into oxidation and reduction, which is what we've done right here. We've got our solid copper breaks into copper ions with 2 electrons. That's oxidation, remember? Leo the lion goes grrr, okay? Or oil rig, oxidizing is losing. Leo, losing electrons, oxidation. And then here we have zinc in the form of an ion, plus 2 electrons becomes a zinc solid. Now it gained electrons, the grr, so it's reduced, okay? Or rig, reduction is gaining, okay? So we got that. We broke that down. Now notice how many electrons are being exchanged here. It's 2 electrons that are being exchanged. So if we have 1 mole of copper, okay, and 1 mole of zinc, guess what? We're going to have 2 moles of electrons that are being exchanged. Now that's going to be an important thing later on, especially when we deal with the Faraday constant. Okay, so from the table of standard reduction potentials, we're going to find the potential for our cell, taking into account the oxidation reduction. So this is from the table that we would get. They would give you that information. They are not going to have you memorize the table. That is crazy, or cray-cray. Okay, so the potential of our cell is going to be the potential of the reduction plus the potential of the oxidation combined, which is what we have here. Now, in this case here, you may notice that both of these happen to be negative. Now, the fact is, if you look on the table here, this, if it were to go from copper 2 plus 2 electrons, it gets solid copper, this would actually be a positive number. But that's not happening. We have to flip it. That's why it's a negative instead of a positive number if you were to go and look in the book. So you add them together and the entire potential of the cell is about almost negative 1.2 volts. Okay, this is not a battery that we're going to power our calculators with. It's not happening because it's not generating electricity. It's negative, remember that. Okay? So now we've got our number of moles, we have got our Faraday constant, we also figured out our oxidation reduction, we figured out the potential, the cell's potential. We said, hey, it's not galvanic, it's electrolytic. Okay. So now we can go in step 3, we can find our delta G. Well, remember, our delta G is equal to negative N times F times the E of the cell, or delta G is equal to negative times the number of electrons, the moles of electrons, times Faraday's constant, times the cell's potential, okay, which we found earlier. So when we plug this in, we've got our information. We have our negative 2 moles. So right here, this is going to be our N. Right here, this is going to be our Faraday constant, about 9.65 times 10 to the 4th coulombs per mole of electrons. Okay, and coulombs is a charge. Okay, whereas here for 2 moles our N is 2 because we have 2 moles of electrons going through, multiplied by, well, in this case, this is the cell's potential. Okay, so that's where it is. We multiplied it out, and we've got delta G is equal to about 230, a little over 230 kilojoules. As a result. So here's the thing, given what you know about delta G, all right, if delta G is negative, the reaction is going to be spontaneous. If it's positive delta G, it's non-spontaneous. We're not going to have a lot of we're not having a whole lot of that. So delta G is positive. So the reaction isn't spontaneous. Now the other thing is, ladies and gentlemen, so we know that delta G is positive, but here's the question. Will the zinc form a solid on the copper electrodes? No! Because the reaction needs to be spontaneous in order for that to happen. And guess what? Delta G is positive. It is positive, so there's no way that the zinc is going to plate out. It's not going to form a solid. So our final answer here, ladies and gentlemen, is delta G is about 230,000 plus joules. Okay, and our second, that's our first answer, it's non-spontaneous because it's delta G is greater than 0. And here we got zinc ions will not plate out because the reaction isn't spontaneous. Hey, I'm hoping that you guys would take advantage of this, and I hope that this has helped you guys out, because this is something about dealing with electrolytic cells. Okay? And I wish you guys the best. This is Jacob Fonseca